Welcome to this Concept Explainer, brought to you by CBSE ScoreLab of ProfSam.com. That is ProfSam.com. Today we are taking a deep dive into the bar magnet from Unit 5. Magnetism and matter. Our mission is simple: to take these crucial concepts and provide a simple, exam-safe explanation that you can truly understand and, remember for life.
I am ready. Magnetism has always felt slightly mysterious to me,
Yeah.
especially why some things are permanently magnetic and others just aren't.
Well, that mystery vanishes today, I promise. Once we look at the physics behind it, it's actually quite logical. Okay, let's start with a simple question. We have all played with magnets, right?
Of course.
Now, what if you take a really strong magnet and heat it up? I mean, really heat it until it glows red hot.
Sure.
What do you think happens to its power?
That's a curious question.
Can heat actually destroy magnetism?
My guess would be maybe it gets weaker, but it shouldn't disappear completely. I mean, the material's still iron, the atoms are still there. How can it just vanish?
And that is the surprising fact. And this is the absolute core of our deep dive today. If you heat a permanent magnet, like a compass needle, above a certain temperature, it completely loses all its magnetism. It becomes just a regular piece of iron.
Wow, completely.
Completely. The atoms are there, the iron is there, but the attraction is gone. This tells us something crucial. Magnetism in a bar magnet is not a permanent property of the individual atom. It is purely a property of organized atoms.
But organization is everything here.
Organization is everything. The heat just provides enough energy to shake up that internal organization, and poof, the magnetism disappears.
That sounds like it's a collective effort then, not something each atom does on its own.
Exactly right. That's the perfect way to put it. So let's formalize that core idea. Magnetism is created by moving electric charges. Mostly, it's the spin of electrons inside an atom. A bar magnet is basically a solid material where billions and billions of these tiny atomic magnetic effects, we call them magnetic dipoles, are all forced to align to point in the same direction.
Okay, so it's organized, collective magnetism made visible.
Made visible and tangible, yes. To help you visualize this, let's use an analogy. Think of a huge crowd in a stadium, let's say 50,000 people. Each person is like an atom's magnetic dipole.
Okay.
Now, if everyone is just walking around randomly, some going left, some right, some in circles, what's the net motion of the crowd?
Zero. It's just chaos.
Exactly. Chaos. No net motion, no collective power. But now, what if all 50,000 people start marching together, shoulder to shoulder, in the exact same direction?
Then the force would be enormous.
Yeah.
A single, powerful movement.
That's a bar magnet. The atomic people are organized and aligned, creating that strong collective magnetic force we can actually use.
That analogy really helps. So a permanent magnet is strong because all of the atomic dipoles stay aligned.
Exactly. They stay aligned. And now we can use that idea to build a mental image. Imagine the bar magnet is a crystal lattice, and inside each atom there's a tiny arrow that's the magnetic dipole. In a normal, non-magnetized piece of iron, these arrows are all pointing in random directions. Total chaos.
Right.
But in a magnet, it's like a giant hand has come and aligned all those arrows to point the same way. The South Pole is where all the arrows point into the material, and the North Pole is where they all point out.
Understood. So now that we have this microscopic picture of aligned atoms, let's see what the insert textbook says. How does it define the properties we can actually observe?
A perfect transition. Let us confirm these fundamental properties by looking at the formal definitions. Could you read out the standard properties we need for the exam?
Of course. I'll read from the text. First property. When freely suspended, it points in the north-south direction. The tip pointing to the geographic north is the North Pole, and the tip pointing to the geographic south is the South Pole.
Straightforward. That's just how we label them. What's next?
Second property. There is a repulsive force when north poles, or south poles, are brought close, and an attractive force between opposite poles.
The classic rule. Likes repel, opposites attract. And the third point, this one is the most important.
Yes. We cannot isolate the north or south pole of a magnet. If a bar magnet is broken, we get two smaller bar magnets, and it adds isolated magnetic north and south poles. Monopoles do not exist. This is the part I find a bit confusing.
Yeah.
If I cut a charged rod, I can get a separate positive piece and a negative piece. Why can't I do that with a magnet?
That is the absolute key difference between electricity and magnetism, and understanding this gets you full marks. Magnetic poles are not charges. They are just regions where field lines exit or enter. The real story is revealed by the magnetic field lines. Let's go step by step. Step 1. We observe that field lines exit the North Pole and re-enter the South Pole, but this is outside the magnet.
Okay.
Step 2. The density of the lines shows the strength. Denser lines, stronger field. Simple enough. But step 3 is the fundamental rule. Magnetic field lines must form continuous closed loops. They cannot start or end.
Unlike electric field lines, which start on a positive charge and end on a negative one.
Precisely. Now, think about the consequence of that rule. For the loop to be closed, what must happen inside the magnet?
For it to be a loop, the lines must travel from the South Pole back to the North Pole inside the magnet.
Exactly. They run from south to north inside the magnet, completing the circuit. So if you cut the magnet...
I see. The new face you just created instantly becomes the opposite pole needed to keep the loops closed. The system has to maintain that continuous flow.
You've got it. That's why monopolies can't exist. The closed loop is fundamental. Hope everything is clear so far. This concept explainer is from ProfSam.com. That is ProfSam.com.
All right, so now that we've established the physical reality of the closed loop, let's look at the math. A bar magnet has two opposite poles, so it acts as a magnetic dipole.
Just like an electric dipole. But instead of an electric dipole moment P, here we use the magnetic dipole moment, which is written as M or sometimes mu.
Correct. The magnetic dipole moment, let's call it mu, is a measure of the magnet's overall strength. When you place this dipole in an external magnetic field, B, it experiences a torque, a twisting force.
And that torque is what tries to align the compass needle with the Earth's field, right? Perfectly said. The formula for this torque is pow, mu b sin theta. Theta is just the angle between the magnet's moment and the field. Let's do a very quick example. Imagine a small compass with a magnetic moment, a mu of, say, 0.5 am.
Okay.
We place it at a 30-degree angle to the Earth's magnetic field, which is roughly $50 times 10 seconds Tesla. We just plug in the numbers. Torque is sin 5 times 50 times cum6 times 30 circ.
And sin 30 is just 0.5 or 1/2.
Right, so it's $5 times 50 times 10⁶ times 0.55.
Which comes out to $12.05 times 10 Newton meters. That seems like a really tiny amount of torque.
It is tiny, but it's more than enough to slowly rotate that lightweight compass needle until it lines up perfectly. And this whole concept, the fact that these field lines form closed loops, directly leads to a fundamental law of physics, Gauss's law for magnetism.
It basically says that since there are no monopoles to start or end on, the net flow, or flux, through any closed surface has to be zero.
That's the one. Whatever field lines go in must come out. This observation is crucial. Now let's move on to some common mistakes. Let's discuss 3 silent killers. These are misconceptions that can cost you marks in exams. Killer number 1, the pole charge confusion. The wrong idea is that magnetic poles are just like electric charges.
Students think that because, opposites attract and likes repel.
Exactly. But the correct idea is that poles are not charges. Remember, cut a magnet, you get 2 new magnets, not 2 separated charges.
Right, so if I cut a magnet, I can't isolate the North Pole. The new face just becomes a South Pole to keep the loops closed.
Perfect. Killer number 2, the Earth's pole confusion. The wrong idea. A compass's north pole points to the geographic north, so Earth must have a north magnetic pole up there.
The naming is so confusing.
It is. The correct idea is that the magnetic pole near our geographic north pole is actually a south magnetic pole.
Of course, a compass needle's north pole would be attracted to a south pole. It's just simple attraction.
That's all it is. And killer number 3, this one gets people on diagrams all the time. Internal field direction. The wrong idea is that inside the magnet, the field lines also run from north to south, just like outside.
Because they just assume the direction is the same everywhere.
Yes, but we know better. The correct idea is that field lines are closed loops. So inside the magnet, they must run from south to north to complete that circuit.
Inside, south to north.
Yeah.
Outside, north to south. Got it.
Excellent. Now, to make sure these facts are locked in, let's use some memory anchors. To remember the internal flow, use the mnemonic SNAN, S-N-A-N. It stands for south to north inside. It sounds a bit like scanning.
SNAN. Okay, I can remember that.
For the external pattern, just use a catchy phrase. Out at north, in at south, the flux exits the north face.
Yeah, clear.
And finally, a physical gesture. Use your right hand. Curl your fingers like the field lines, starting from the North Pole and curving around to the south.
Okay, like I'm tracing the outside field.
Yes. And then, to represent the internal field, push your straight hand right through the middle from your wrist to your fingertips, going from south to north. This gesture helps you feel the complete closed loop.
That's actually very helpful. The motion makes the concept stick.
Good. Now let's recap the 3 most essential points you must know for your exams. Point 1. A bar magnet is a macroscopic effect of billions of aligned atomic magnetic dipoles. Heating or shock destroys this alignment.
Alignment is key.
Point 2. Magnetic field lines form continuous closed loops. They exit north and enter south on the outside, but run from south to north on the inside.
The closed loop rule.
And point 3. The non-existence of magnetic monopoles means the net magnetic flux through any closed surface is always zero. This is Gauss's law for magnetism. To get maximum marks in 12th CBSE Physics, Chemistry, and Maths, visit ProfSam.com.
That is PROFSam, right, Zach?
Yes, exactly. ProfSam.com. Thank you for joining this deep dive. And before we go, here's a thought to mull over. If all moving charges create magnetism, and everything in the universe is made of moving charges, is there anything that is truly perfectly non-magnetic? Something to think about.